Hello, welcome to the code elaboration. So, as mentioned in the video, these two files are relatively naive. I mean, most of what they're doing is effectively making a system call, right? Even this scapy.ar ping is really just making an iterative system call for a range of IP addresses, right? So, I'm not going to spend too much time on these. The only thing I'm going to say here is this is important, right? So, echo 1 proxies, net value, all this stuff forward. I mentioned in the video, this effectively allows the device that it's instantiated on, right? In this case, it's my laptop. It allows it to, like it says, forward IP data through it. So what I'm doing by instantiating this is or toggling this, I guess is a better way to say it, is I'm I'm becoming the router because the real router, the wireless router, will send data with intention of it continuing down the chain to, in this case, it was that 172.16.104.128, right? So this turns me into a passive observer. If I set myself up as a man in the middle and then turn this off, it breaks stuff or it gets kind of weird. But I talked about this. This is relatively straightforward, right? Going into sniffing and modifying packets is a little different though. So we'll get to this class. This is a converter, so we'll get to these in a moment. But the big thing are these two functions, these three functions. So these packets contain three different layers that we're analyzing, right? So there's this Ethernet head, which if you're in Scapy is denoted by capital E, ether, as a function call. Will return this kind of data. There's IPv4, which similarly is just IP in Scapy talk, and then TCP, which is TCP, both of which are all uppercase. But what we're doing here is we're actually this is a slightly different approach, but it allows us some more flexibility throughout, so it pays off. But what we're doing here is we're creating a socket actually when we start up this program, and all it does is just reads in, this is a buffer size, into um, this broken up tuple effectively is what we're doing, right? It returns a tuple, we're splitting it in half. And then we're just going to pass this data down the chain of command, right? So we take raw data is just bytes. I mean, it is completely unstructured in this case. And we unpack it, give it some parameters, right, on what to expect from the data. And then we give it a data range in this case, right? The first 14 bytes are what hold the Ethernet head. So we're going to parse this out into a destination, a source, and a prototype, and um, return that with the data, right? Data is just everything beyond our header, right? And so you'll see here our main call. ETH is Ethernet head raw data. And then we check to see if ETH2 is 8, right? If our protocol or prototype, sorry, is 8, that means we're talking about IP stuff. So we're going to go ahead and actually pass it ETH3, which if you recall is the data, is just the rest of the data. So we're going to pass that down the chain of command to IPv4 head. We're going to get the version, right? So in this case, it'd be 4. We have to do some bit shifting and some, this is just ANDing with the first 4 bits. We have to do some dumb BS just because we're working with raw bytes here, but this converts it into processable data. And then we're just going to go ahead and unpack all of this data, right? So TTL, like a time to live kind of thing. We've got our protocol, we've got source, target, and data, right? So it's very, very similar to Ethernet head. We're just pulling some more stuff out of it. And from there, we can get our version, we can get our header, and get all of the necessary data, right? Source and target in this case are still raw bytes. So if we want to interpret these visually, then we are going to have to do some data processing on that, but I'll get to that in a moment. And then I'm sure, as you can assume, similar to checking to see if we're working with IP protocols, then calling IP, we're going to check to see if we're working with TCP layer protocols, right? So protocol 6 under the IPv4 head is TCP data. So we're going to pass it our data return, and we're going to parse out, in this case, we're looking for flags for the most part, right? So we're getting source and destination ports, which is good. Sequence ACK numbers, which is what we need. And then this offset reserved flags is just kind of saying it's a pointer is kind of a bad way of doing it's a packaged byte, right? Where we can pull flags out of it. So I actually made a class to house all of this. And it literally just has 6 integer methods within it. Right, we've got our 6 flags: urge, act, push, reset, sync, and fin. That's a termination thing, and we're just gonna set all of them, right? So offset, we're determining our offset again, more bit shifting stuff that we have to do. And then these flags, like I mentioned, we literally just and it with in this case, this is gonna be the bit position, really, that we want, and then we're just moving it relative to where it needs to go, right? So 2 to the 5 is 32. So these correlate directly, and we're just going to kind of make our flags out of that. And then we're going to take the data and we're going to parse that out. And from here, that gives us this print packet function with all the data we need. And this just is, just literally just a series of print calls that take all of the data we're putting in. It does kind of put it back in the format that it came from, but in this instance, it's now been processed, and so we can actually visualize it a little easier. The most devious part of this whole file is actually getting the MAC and the IP addresses. So for whatever reason, Python, both 2 and 3, I tried this in both versions, will randomly interpret certain bytes as ASCII or Unicode strings, like data. And it has to do with the bytes leading up to it instantiating like a trigger, basically, for recognizing ASCII or Unicode or, even like Latin 1, which is what a lot of things are encoded in. Stuff like that. And so what will happen is if I try and just print out a bunch of bytes, I don't actually just get a bunch of bytes. I get like this half interpreted thing. And so to prevent that, I take in a raw, I called it raw string, but it is bytes. And I cast it into a custom hex string function, which will return hex values without the 0x tag in front of them, separated by a space. And I'll convert those into a list. And what that allows me to do is just effectively do nibble-wise processing over kind of pseudo through a string, right? So this just makes it into MAC address data, right? So for ion range, we're starting at 2 because we don't need to iterate from the beginning. And then I have to take the length of this process string and then add the length of the process string divided by the number of, like the size of each unit, which in this case we're doing bytes, so it's by 2. And this 3 is like our increment. So this is kind of a very convoluted way of doing it, but effectively what's happening is we're going to be inserting into this process string, this thing that we're iterating over in the first place. So because of that, we can't just do for int in range, right, 2 to the length. We have to add this kind of buffer on the end and then change our increment so as we don't place these either too narrowly, right? We could do like every nibble, but that wouldn't look right, or we don't hit an index value error. And so we just insert these into our list, and then we join all of it together, right? Similarly, to get our IP addresses, we do the same hex string conversion, which I guess I will talk about real quick. It literally just takes raw hexes and puts it in a list, interprets it as a string with a pad, right? So this :02 hex means we're going to pad with zeros to a width of 2 and interpret it as hex. This is literally all that means. And then we're going to add this to bytes, and we're going to return bytes. Right. So our IP address, similar to our MAC address, we've got this kind of strange iterator. But instead of everything being a hex now, we need to separate by a period. And at this point, what we'll get is the hex values of each sub string within an IP address. And then we just take that, join it, and then resplit it. So we're just kind of changing how we're contextualizing what's going on here, right? From a list of each individual element, whether it's a hex value or a period, it's just treating them as characters, so it doesn't actually matter. And then we're gonna split it back apart at the period so that we can collect the bytes. And then for each of those, we're just taking it and interpreting as an integer in base 16, casting it back into a string, and then joining it back together. So it's kind of circular. There's definitely better ways to implement this, but this works, and I was just kind of getting to the point where I was tired of working with Unicode errors, and I just wanted it to work. So I did. I made it work. So that's all this does, and I think the header looks pretty nice. Like I was impressed with how it came out. As you saw in the demonstration, I can get it pulled up real quick. It's formatted pretty nicely, right? And so that is nice. It makes it really easy to read what's going on, right? So, one moment. I don't have my other VM up. Oh boy. Okay. Well, that's pulling up. Oh, it pulled up. Okay, well, this is initializing. We'll look at the other thing and then get an example pulled up. Just so we can see a direct correlation between the print statements that we're seeing and how they actually turn out. There we go. Okay, you're attacking on network data. Are you? Well enough that I can pull this. So if we hello. There it goes. This recording is definitely putting a toll on my computer. There we go. There we go. We're spoofing. Thank you for your patience. So if we go ahead and run uh, this program, this is in Python 3. There we go. Perfect. That's exactly. So yeah, you can see kind of an output of like we've got our different layers that we're looking at, right? Our Ethernet kind of layer or frame, however you want to think of it. Our IPv4 layer, and then underneath that our TCP layer. And you can see this is, I mean, all this data looks very nice. It kind of packages well, and it's easy to look at, ignoring the fact that there are a lot of packets, right? But that's that. This is a great data collection methodology, as an expansion onto packet modification and stuff like that. This is the data you would need to effectively hijack a port and open it up so you can effectively cut someone off from the internet. And on their end, it just looks like their service has been interrupted. But what you're actually doing is redirecting that port to a listener you've set up, right? A netcat listener, for example. And so this has some very powerful information. We can do a lot with this. So that's cool. I like that. Let's look at, oof, come on. Let's look at our packet modification and show what kind of protocol, like what precautions are being taken already and how that is kind of impacted by the network structure that the router is communicating through specifically, right? Because my computer is, wait a moment, this thing is throwing a fit. There we go. My computer is connected to university Wi-Fi. So what's happening is, in order for the router to connect to the internet, it goes through that first. And that is definitely layering the packets in a way that is effectively corrupting them, which is very interesting. It's a nice resistance to packet modification, because on non-UYO networks, if you set this to from 80 to 8080, which is HTTPS communication, this thing chokes. This thing works. And so it's very interesting to see the differences between different network configurations and what that actually what that means. So this thing is being very slow on me. There we go. Let's see if we can grab any port 80s. Oh, perfect. There are right at the end here. So like I mentioned earlier, we're not actually talking on a standard HTTPS port. And so I had to kind of modify my attack a little bit to tailor towards that. Port 80 is usually specified for HTTP communication. And so this was a big surprise to me. This really kind of threw me for a loop a little bit, just because I was really not expecting, I didn't know how to handle it, because if you break down these packets on 80, they don't contain HTTP data. They're definitely HTTPS or HTTP 1.1, right? Is how that's specified in the packet. Goodness. And that very much exists on this port, which I think is, I don't know, I think it's very cool. But so the first thing we do is we check to see if this has a raw layer, right? If there's data being transmitted specifically. In this case, thanks for scooting down on me, I guess. In this case, our data is hex or bytewise. And so we have to kind of be aware of that, but that's, that's okay. That's standard. And then all we're doing is checking. This is not the most efficient way to do so, but it's readable, and I don't know, I kind of prefer it. So if our packet that we defined, right, the Scapy IP packet, if it has a TCP layer and that TCP port is 80, we're going to do stuff with it. So D port, S port, destination, and source. I print out just some information for me to help debugging. And then what would happen under standard network protocols, right, is this packet. So we're basically just substituting, making a regex call for the accept encoding portion of this packet, and then followed by anything. We don't care what it is. We just want to go until we hit this return and new line, because this is where things terminate, and we don't want to just fill out the rest of this packet with nothing. But we're gonna fill effectively the rest of this line with nothing. And what that allows us it breaks down the S part of the HTTPS protocol, right? So it'll allow um, any type of packet type. We can zip, we can pass it like rendering data, we can pass it kind of whatever we want. Files, it doesn't matter at this point. And we're replacing it within this load that we have, right? And so similar to that, our payload, we're also going to replace HTTP 1.1, which is the like HTTPS kind of framework, to 1.0, which is unprotected. It's very much a raw type of connection. There's a far less sanitization going on with 1.0. And so we're doing this for packets that we are, great job. We're receiving, right? So what's going to happen is the network is going to say, okay, this is the kind of packet we're going to expect to receive. So if we can change that, then we can kind of frame our attack a little bit. And so what we do here is we then check the source port, and all we're doing is we're defining this injection code just so it's easier to pass around. But all I'm doing is creating a JavaScript alert, right? And all we're going to do is replace the body closer in the raw HTML with the script call followed by the body closer. So we're just going to insert it as the very last thing. That way we know we're not interrupting any rendering or anything like that. If I didn't make this an alert, it would go largely unnoticed, right? So all we're going to do then is update the content length, right? So we no longer are able to say that this is a correct value because we've changed the length, right? So we're going to pull the content length out, and then we're going to just check to make sure we're talking about text HTML stuff, and then we're going to update it, right? So this content length check, group 1 will pull this, and all we're going to do is make a new one where we take this as an integer, and we just add the length of our injection code. And so when we reassign this to the payload, what will happen is it'll send the packet back saying, yes, this is the amount of data you should be expecting, even though that amount of data is not what the network sent us. And then all I do at the very end here, just because this portion was highly repetitive, is if the payload has been modified, right? If it's no longer this scapy raw.load, we're going to make a new packet where we delete all of these verification things for them to be automatically regenerated. And we're just going to set the payload to this new packet. And packet.accept is a function of netFilterQ. And all this means is we're going to pass the packet on through the device as if it's a router. So I really am interested to continue this and just kind of break this code down more and maybe see if I can tailor an attack specifically for this type of network, right? So the university network uses PAP tunneling and with that MSCVH whatever V2. So we've got asymmetrical encryption protocols being enacted on the network for verification, as well as experimentally some very clear detectors of network spoofing and kind of manipulation going on. So I'd be very interested to see what's going on here within, obviously trying not to get flagged by security or anything like that. It's not worth it. But yeah, I will continue this, and even if it's not necessarily directly related to this project, I'll probably append to this project anyway and go from there. My goal is to start by getting websites to render, but I would like to instantiate a full reverse shell. I might have to do some implementations in either Perl or PHP maybe. I need to be able to take the port that's being used currently and tell it to kind of redirect to doing something else. And that can be very tricky, Diane, but especially with well-defined ports, right? The private, less than 1024 level ports. Those can be very tricky to manipulate, but it'd be very interesting experimentation. So we will see. Thank you very much. Yeah, bye.